Input interface. What is meant by input? What is meant by output? What is meant by interface? So input is nothing but whatever the input we are giving, using our input device will be giving that. So output in the sense after processing this input, you'll be getting the output through the output device. So intermediate, some interface is there to transfer the information. So the method which is used to transfer information between the internal storage and external input-output device, we are telling that as an input-output interface. So interface in the sense which is in between. So in between this input-output device, we are telling that method of transformation as input-output interface. So there exists a special hardware components between CPU and peripherals to supervise and synchronize all the input and output transfers. So that one we are telling as an interface units. So what are the modes we can transfer the data? So normally the binary information which we are receiving from the external device is usually stored in the memory unit. So the information which is transferred from the CPU to the external device is originated from the memory unit 1. So the CPU will merely process the information, but the source and target is always the memory unit 1. So from where it needs to get the data, so that will be the memory unit. To where it will get stored, that is also what from the to the memory unit. So the data transfer between the CPU and the input-output device may be done in different modes. Okay. So what are the modes? The data transfer to and from the peripherals may be done in one of these three possible ways. So what are these three possible ways? So one is programmed input output, interrupt initiated input output, direct memory access. That is using our DMA. So what is meant by this program input output? So it is due to the result of the input-output instructions which is written in the computer program, this program input-output will occur. So each data item transfer is initiated by the instructions in the program only. Usually, if you are transferring the data from the CPU register and memory, and in this case what happens, it requires a constant monitoring by the CPU of the peripheral device. So the example for this program, the input output, in this case, the input output device does not have the direct access to the memory unit. So the transfer from the input output device to memory, which requires the execution of the several instructions by the CPU, including the input instructions to transfer the data from the device to the CPU, and it will store the instruction to transfer the data from CPU to memory. So it's like vice versa. So in program input output, what happens means the CPU stays in the program loop until that input output unit indicates that it is ready for the data transfer. So this is actually a time consuming process since it needlessly keeps the CPU busy. So these situations can be avoided by using the interrupt facility. So what is meant by interrupt? So when a device is ready to communicate with the CPU, okay, it will be generating one interrupt signal. I am ready, like that it will be generating the signal. So the number of input output device which is attached to the computer, and each device is able to generate the interrupt request. So the main job of the interrupt system is to what? To identify the source of the interrupt. So there is also a possibility that several devices will request simultaneously for this CPU communication. So then the interrupt system will decide which device is to be serviced first. So many input-output devices will be giving the request, but this interrupt system only will be decide which device I need to service first. Okay, so this is about the interrupt and interrupt request. So what is meant by this interrupt which is initiating this input output means it is necessary that computer system should give the response to device like keyboard, sensors or whatever other components when they request for service. So the event that causes that interruption is called the interrupt and the special routine executed to service. This interrupt is called the interrupt service routine. So when we are giving when the CPU when the input output system is giving some interrupt request to the CPU for some work means after receiving that request, the CPU will be giving the acknowledgement to the input output system. So the interrupt service routine, that is our ISR, is different from this subroutine, or it is available in the interrupt vector table. That is our IVT. So normal program can be interrupted by three ways. One is by external signal, and another is by a special instructions in the program, and another is by the occurrence of some condition. So an interrupt caused by this external signal is referred to as the hardware interrupt. And the interrupt which is caused by the special instructions or some condition is referred to as software interrupt. So what is meant by interrupt hardware? So an input-output device requires an interrupt. Okay. So how this interrupt is classified? It is classified as single level interrupts. Single level interrupts in the sense many interrupting devices. It may be an input or output device. Many interrupting device and all the interrupt requests which is requested by these input output device are made through the single input pin of the CPU. So if it is through a single input pin of the CPU, that type of interrupt will be coming under the single level interrupt. So what about this multi-level interrupt in the sense the processor has more than one interrupt pins. The input-output device are tied to the individual interrupt pin. Thus, the interrupt can be immediately identified by the CPU upon receiving an interrupt request from it. So in single-level interrupt, what happens? Many interrupting device which is sending the interrupt request will be made in the single input pin. But this multi-level interrupt, what happens means each interrupter device will be having the individual interrupt pin. So which interrupts is which request is coming? So based on that interrupt can be immediately, which is identified by the CPU upon this interrupt request. So this is about this single level and multi-level interrupts. Okay. So using one diagram, we are just explaining the single level interrupt. So as I said previously, if many input or output device, when it is sending the request, it will be connected to the single interrupt pin. So see here, what happens, input output device. So here we are taking as I1 and then input output device 2. Okay, where interrupt like I2, like that we having n number of input output device. So when it is sending the request, okay, which is connected to this gate, where it will be connected, where it will be giving as a one input as a which is connected to the individual, not individual, to a single input pin. So that only we have stated previously. So all interrupt requests are made through the single input pin. Okay. And here this will be connected to the input output interface. Okay. So where the bidirection. So this symbol indicates bidirection. So the data will be transferred from CPU to this input output device and from here to here. So single level interrupt in the sense many input output device where it is sending the interrupt request which is will be connected to the single input pin of the CPU. So that is about the single level interrupt. So next is our multi-level interrupt. So what is meant by this multi-level interrupt in the sense means here input output device we having like n number of input output device we having which will be sending again the interrupt. But here which is not connected to the single input pin where individual interrupt pins will be having for this multi-level interrupt. So see here, individual interrupt pin we having. So n number of input-output devices there means we'll be having the n number of interrupt pins. And again here also it will be connected to input-output interface and to the data bus. So this is about what? Multi-level interrupt. So next is what now? Vectored interrupt. So if the internal control circuit of the processor produces a call, okay, to a predetermined memory location, which will be the starting address of the interrupt service routine, then that address is called as a vector address. And that type of interrupt is called as a vector interrupt. So what are the two ways to support that vector interrupt? Means we having fixed vector address and then programmable vector address. So next is what now? Your interrupt priority. So many input-output device will be giving the interrupt request simultaneously. So when these interrupt requests arrive from two or more devices simultaneously, the processor has to decide which request should be serviced first and which one should be delayed. So this, based on this request, we need to set the priority. So which one we need to handle first, which one we need to service first, and which one should be delayed. So the processor only will be taking the decision with the help of these interrupt priorities. And it will be accepting the request which is having the highest priority. So this is about this interrupt priority. So based on the highest priority, that particular input or output device which is sending the interrupt request which will be served. So see here, this is a daisy chain concept where we having the interrupt request where each and every device is giving that interrupt request which will be sent to this CPU, that is the processor, and the acknowledgement will be sent from one device to the another. If this acknowledgement is not belongs to this one means it will be sending to next one. So like that, till the end of that particular device, it will be sending the acknowledgement. So if it is connected, in this case, we are telling this as a daisy chain. So what is meant by X? Any event, many events can cause an interrupt. So all such events are called exception. So exceptions can be classified as fault and traps. So fault in the sense, the fault are the exceptions that are detected and serviced before the exception of the faulting instructions. So trap is nothing but another type of exception that will be reported immediately only after the execution of the instruction, which will cause a problem also. So the user-defined interrupt are the best example for this trap. Okay, so before the exception of that faulting instruction, if I'm just servicing means that type of exception we are telling as a fault. And the type of exception which will be reported only after the execution of the instruction, in the sense that type of exception we are telling as a trap. So this is the difference between the fault and trap. So what are the things we saw previously? So we saw what is meant by interface and what is meant by input-output interface. We saw what are the modes of transfer, and then we saw detailing about these modes, and then what is meant by interrupt, and how this interrupt request and acknowledgement are giving, and we having the levels like single level and multi-level interrupt. And based on the priority that interrupt request will be served. And we saw the daisy chain, and we saw what is meant by exception and how it can be handled. So like that, we saw under this previous topic. So under the same topic, input output, we are going to see what is meant by the DMA. So DMA is nothing but it is direct memory access. So direct memory access means the software control data transfer is not suitable for the large data transfers such as data transfer from magnetic disk or optical disk to memory. So in this situation, the hardware controlled the data transfer is used. So hardware controlled data transfer means the external device is used to control the data transfer. External device generates address and control signal required to control the data transfer and allows the peripheral devices, that is the external devices, to access the memory directly. So hence this technique is referred to as a direct memory access. So short we will be telling that as a DMA. So the external device which controls the data transfer on it, we are telling as a DMA control. Okay, so what is meant by DMA? Here the DMA where which is nothing but where we are directly accessing the memory, where the external device which controls the data transfer, we are telling that as a DMA controller. So the software which is controlling that data transfer is not suitable for large amount of data transfer from magnetic disk or optical disk to memory or vice versa. So during that time only we are handling this. So how this DMA in a computer system is used? For example, here we having the processor and we having the main memory, and then using the system bus where the input or output device is connected to the processor or the main memory. So here the disk controller and DMA controller, where many disk we having which is connected to the disk controller, and again the network interface is there which is connected to the DMA controller, and again everything is connected to the system bus. And if we are talking about the main memory, here the printer and keyboard which is connected to this system bus. So using this DMA controller only, the outside network interface will be sending the data to the processor like that. So the DMA is used to connect a high-speed network to the computer bus. So the DMA only controls or handles the data transfer between the high-speed network and computer system. So it is also used to transfer data between processor and floppy disk with the help of that floppy disk controller. So see here we are having the processor, DMA, floppy disk controller and floppy disk drive. So if I'm just inserting the floppy disk in the floppy disk controller drive, in the sense what happens is the data will be the bidirection. So from the floppy disk, the data will be stored to the floppy disk, or from the floppy disk, we can retrieve the data. So only this is bidirectional. Again, the control status, which is what bidirectional. So here we having the address bus, data bus, and we having the control bus. So each three thing is connected to all the devices. So see here, the floppy, when I'm just getting the data from the floppy disk drive, using this floppy disk controller, it will be giving the request, data request to the DMA, direct memory access, and that will be sent to this processor. And when it is received, it is sending the acknowledgement again to the DMA, and it will be giving the data acknowledgement again to the floppy disk controller. And here this data, whether to write or whether to retrieve, that control will be there in this floppy disk drive. And this DMA, where if it is want to have the access this processor, it can give the interrupt request to the processor, and even our floppy disk controller can also give the interrupt request to the processor. So all those things which is connected, all the buses and all which is connected to the memory. So when the system is turned on, what happens? The buses are connected from the processor to the system memory and peripherals. So to read the block of data from the disk, the processes in the series of commands to the disk controller device. So in that case, the floppy disk controller, what is doing, it is then proceeding to find the specified track or sector on that particular disk, whether to read or whether to write like that. So when the disk controller is ready to transfer the first byte of data from the disk, it sends the DMA request, that is our DRQ, which is sending the DMA request to the DMA controller. So what happens? The processor responds to this hold signal by floating its buses and sending out that hold acknowledgement signal that is represented as a HLDA, hold acknowledgement, to this DMA controller. When the DMA controller receives this HLDA signals, it will be sending the control signal to disconnect the processor from the bus and connects DMA controller to the bus. So what is meant by DMA channels? The data transfer is monitored by DMA controller, so which is also called as DMA channels. So in previous case, what happens here, we are just transferring the data. So this floppy disk controller, what it is doing, it is giving the interrupt request to the processor, and as well it is just giving the DMA request also to the DMA. So and it is in the hold position, and after receiving this only, the processor will be sending the acknowledgement of this hold acknowledgement. Again, the DMA acknowledgement will be sent to this floppy disk controller, and again that status will be updated in this floppy disk drive. So this is about this thing. So here, as I said previously, the data transfer is monitored by our DMA controller, which is also called as a DMA channels. So the data transfer mode by DMA controller for the single transfer mode. So the single transfer mode we are telling as a cycle stealing. Single transfer mode we are telling as a cycle stealing. So cycle stealing in the sense a device can make only one transfer after each transfer. So DMAC gives the control of all buses to the processor. Block transfer mode, in the sense this mode is used when the DMAC, that is DMA controller, needs to transfer the block of data. So demand or burst transfer mode, what it will do means this mode continues to transferring the data until this DMAC. Okay, DMA controller is having the inability to continue delivering the data. What is meant by bus arbitration? The device that is allowed to initiate the data transfer on the bus at any given time is called the bus master. In a computer, there may be more than one bus master, such as processor, DMA controller, etc. So the bus arbitration is nothing but is a process by which the next device to become the bus master that will be selected, and this bus mastership is transferred to it. So what are the types of bus arbitration we have? So we having daisy chaining, we having polling method, we having independent request. So what is meant by this daisy chaining? It is simple and the cheapest method. All masters make use of the same line for bus request. See here, we having main n number of masters, where we having the bus request and bus busy signals. So all the masters will be connected with this two thing. So when it wants to access any data during that time, it will be giving the bus request, which will be transferred to this controller, and this controller will be granting the permission. So first it will be granting the permission to master one, but the request is not coming from this device, means automatically the bus grant signal will be transferring that grant signal to the master 2. If that also is not sending the bus request, in the sense it will be giving the bus grant signal to the master n. So like that it will be what now move. So this is about what now daisy chaining method. So what is meant by this polling method? So polling method, in the sense, in this, the controller is used to generate the addresses for the masters. So for each master, it will be generating the addresses. So number of address line required depends on the number of masters. So how many bus lines, how many address lines we want, that will be depend on the number of masters. So which is connected in the particular system. For example, there are 8 masters, means at least we need to have 3 address lines. So how this 3 address lines are 2 power 3. So 2 power 3, that 3 which in 2 power k, 2 power k equal to the number of masters. So that k represents the number of address lines. So 2 power 3 means what? 2 into 2 into 2, that will be 8. So we will be having 8 masters. Okay. So in this polling method, the controller will be used to generate the address for that particular masters. So number of address lines required depends on the number of masters which is connected to the system. So here this is the polling method. So here, as I said previously, how many masters I am having, that number of address lines will be there. And then we will be having additionally our bus request and then bus BCP. Okay. So each one will be connected to this controller. So when it wants to send any data or when it wants to retrieve any data, it will be sending the request. So that will be sent to this bus request lines. And when this is busy, in the sense, during the time it will be sending, it is busy. So during that time it will be waiting and then it will be reading the. So next is what? Independent request. So each master has a separate pair of bus request and bus grant lines. So each pair has a priority assigned to it. So the built-in priority decoder within the controller only will be selecting the highest priority request and it will be setting the corresponding bus grant signal. So independent priority, in the sense we having master 1, 2 till n, in the sense the controller which will be giving the bus grant as request is sent to this controller. So each device will be sending the bus request and according to that it will be sending the bus grant signal to this particular masters. So this is about this independent priority. So next is distributed arbitration. So distributed arbitration, in the sense all device will participate. So in this scheme, each device on the bus is assigned a 4-bit identification number. So the number of bits used for identification number actually depends on the number of device which is connected on the bus. So this is the gate question which is asked during 2013 gate question paper. So here what we are doing means we are considering the following sequence of micro operations. The PC is a program counter where I am storing the content present in this PC to this memory buffer register, that is represented as BMBR. And again the value of X which is stored in this MER, memory address register, and Y to this program counter which is represented by PC. And again memory, whatever the content present in this buffer register, again to the memory. So which one of the following is a possible operation performed by this sequence? They are asking the question. So as I said previously, MBR is nothing but what? Memory buffer register. So memory buffer register means what? That stores the data being transferred to or from the immediate access to. Next is our MAR. MAR in the sense what? Memory address register, which will be holding the memory location of the data that is need to be accessed. So next is what? Program counter. The program counter will be containing the address of the instruction that is being executed at that particular current. So first instruction, what it will do, it will place the value of PC into MBA. So that only happened. Second instruction, what it will do, it will place the address of X into MBA. Third instruction, what it will do, it places the address of Y into PC. Fourth instruction will place the value of MBR, which was old our program counter value, into the memory. So that is about this content, this 4 instruction. So now it can be seen from the first and the fourth instruction that the control flow was not sequential. The value of PC was stored in the memory so that only the control can again come back to the address where it left the execution. So this behavior is seen in the case of interrupt handling. And here X can be the address of the location in the memory, which contains the beginning address of interrupt service routine. And Y can be the beginning address of interrupt service routine. So in case of conditional branch, only our PC value will be updated with the target address, and there is no need to store any old PC value into the memory. So in that case, what happens? Only the instruction fetch and the operand fetch will be happening. So PC value is not stored anywhere else. So we'll be going with what option? B option, where it will be initialization of our interrupt service will be there, and no conditional branching is there. So option C also will not come. So this is about this questions. And next question again, it is asked in 2013, where the following code segment is executed on a processor, which allows only register operands in its instructions. So each instructions can have at most 2 source operands and 1 destination operand. Assume that all variables are dead after this code segment. So this is a set of codes they have given. Suppose the instruction set architecture of a processor has only 2 registers. The only allowed compiler optimization is code motion, which moves statements from one place to another while we are preserving the characters. So what is the minimum number of spells to memory in the compiled code? So we having the option 0, 1, 2, 3 like that. So see here, C equal to A plus B. Okay. So C equal to A plus B, here I am just using the register 2 register R1 and R2. Okay, we are using R1 and R2. So here C equal to A plus B means here the A value will be stored in R1 and B value will be stored in R2. The next instruction is D equal to C into A. So D equal to C into A in the sense, I'm just having doing all the calculation and again I'm just storing in R2. So that I'm taking as C. Okay. I'm just going to multiply C with A. So C with A. Okay. And then again I'm just storing that in what? D. Okay, so I'm just taking as X. So that D I'm just taking as X. So here A and X, but we will have to store that C in the memory. So we don't know if X is greater than A. or not. Another line we having like C into C. So that is what A into A. I'm just storing the values in R1. So I'm just taking as A into A and just storing that in Y. So I need to choose the best case of whether X is greater than A. So the minimum spill will be what now? Only 1. So what is meant by this spill? The computer can quickly read or write registers in the CPU. So the computer program runs faster when more variables can be in the CPU register. So this process only we are telling as a filling the registers. Okay. Having doubts? So next is 2013 again the paper where we are considering the same data as our above questions. So what is the minimum number of registers need in the instruction set architecture of a processor to compile this code segment without any spill to memory? So do not apply any optimization other than optimizing register allocation. So the values they have given like 3, 4, 5, 6 like that. So here note that for solving the above problem we are not allowed for code motion. So we will start analyzing the code line by line and determine how many registers will be required to execute the above code snippet. So assuming the registers as numbered like R1, R2, R3, R4, we are just analyzing which is shown in the table below. So see here, C equal to A plus B. So A and B, so R1 and R2. So I'm just storing the value of A in R1. I'm just storing the value of B in R2. So A plus B means what? R1 plus R2. And again, I'm just storing this R1 plus R2 in R2. Okay. So next, D equal to C into A. So output of the previous statement, I'm just multiplying with A. So this one is R2 into R1. So what is the, for A, I'm just representing the register R1. Okay. So R2 into R1, I'm just storing that in R3. Again, E equal to C plus A. So here, C which represents R2. So R2 plus R1. So I'm just storing in R4. So X equal to C into C. So R2 into R2. I'm just storing in R2. So here we compare R2 and R1. X greater than A. I'm just doing that comparison. When that is true, I am going to multiply A. So A into A, I am just storing in Y. So R1 equal to R1 into R1. I am just multiplying two values and again storing in the same register itself. Hence, I need to multiply D and then I am just storing in again D. So R3 equal to R3 into R3 and E equal to E as fixed E and just representing as R4 equal to R4 into R4 because E and just representing using the register R4. So from the above analysis we can conclude that at least we need a minimum of 4 registers to execute the above code snippets. So at least 4 registers I want for these for these instructions. I'm just going with the option B. So next, the amount of room need to implement a 4-bit multiplier is the amount of room needed to implement a 4-bit multiplier is 64 bits, 128 bits, 1 kilobits or 2 kilobits. So normally for 4-bit multiplier, there will be 2 power 4 into 2 power 4 combinations. So totally 2 power 8 combinations. And also the output of that 4-bit multiplier will be what? 8 bits. 2 power 8. So 2 4-bit multiplier in the sense 2 power 4 into 2 power 4, it will be 2 power 8. So 4-bit multiplier output, that will be what? 8 bits. Thus the amount of row needed will be 2 power 8 into 8. So 8 we can convert this as what? 2 power 8, and this 8 I am just converting as 2 power 3. So it will be 8 plus 3, it will be 11. So 2 power 11. So 2 power 11 means my answer will be 2048 bits. Okay, so 2048 bits, where which is equal to 2 kilobits. So next, the hazards. The pipeline hazards are the situation that will be preventing our next instructions in the instruction stream from executing during its designated clock cycle. These hazards we saw in our previous class also. So any condition that causes a stall in the pipeline operation, that only we are telling as a hazard. So data hazards occur when the instruction that exhibit data dependence, which will modify the data in different stages of the pipeline. So ignoring the potential data hazards can result in the race conditions, which is also termed as race hazards. So right after read, that will be represented as WAR, which is an anti-dependency, and after right after write, that will be represented as WAW, which is an output dependency. So all those things will be coming under this hazard. So one example, one question here, the register renaming is done in pipelined processor, which is renamed as an alternative to register allocation at compile time, or for efficient access to function parameters and local variable, or to handle certain kinds of hazards, or as part of address translation. So what one we need to choose? So to handle certain kinds of hazards, because register renaming is done to avoid our WAR. So what is meant by this WAR? So as I said previously, WAR is nothing but write after read. So what is meant by this WAW? It will be write after write. So this register renaming is done to avoid this write after read and write after write data. So next example, next question. Consider a hypothetical processor with an instructions of type load. Okay, so LW load R1, 20 of R2, which during the execution reads a 32-bit word from memory, and it will be storing it in a 32-bit register R1. So the effective address of the memory location is obtained by the addition of a constant value 20 and the contents of the register after. So which of the following best reflects the addressing modes which is implemented by this instruction for operand in memory? So we need to choose one option. So by seeing this instruction itself, which is a indexed, using the base value, so we can have one conclusion here. Which one of the following reflects the addressing mode which is implemented by this instruction in the sense? It will be having base index addressing. Okay, so this is the addressing mode for this instruction. So next, a file is organized so that the ordering of data record is the same as or close to the ordering of data entries in some index. Then that index we are telling as a clustered. A file is organized so that the ordering of data records is the same as or close to the ordering of data entries in some index. Then that index only we are telling as what means cluster. Okay. So next, Consider the following consider the following processes where n stands for the nanosecond. So assume that the pipeline registers have zero latency. Okay, zero latency. The latency is nothing but what? Is a delay between a user's action and the web application response to the particular action. So often referred to in networking terms. We are telling this as a latency, as a total round trip time it takes for the data packet to travel. Okay. So see here for this question, where P1, that 4-stage pipeline with stage latency 1 nanoseconds, 2 nanoseconds, 2 nanoseconds, 1 nanoseconds. And again P2, 4-stage pipeline with stage latency 1 nanosecond, 1.5, 1.5, 1.5. And P3, 5-stage pipeline with stage latency 0.5, 1, 1, 0.6 and 1. And for P4, 0.5, 0.5, 1, 1, 1.1. So I need to calculate which is the highest peak clock frequency. So which processor I need to calculate. So the clock period, which is represented as CP, where the formula is maximum stage delay plus overhead. So when I'm taking this first one, 1, 2, 2, 1, which is the maximum 2 nanoseconds. For second 4-stage pipeline, out of this, which is maximum 1.5. And for third one, out of which is maximum is 1. And for P4, which is maximum is 1.1. So here I need to have as frequency directly proportional to this 1 by Cp, that is frequency directly proportional to this this 1 by Cp, that is clock period, or we can say frequency is inversely proportional to this clock period. So at least a clock period will give the highest peak clock frequency. So f of P3 in the sense 1 by 1 nanoseconds, which will be giving the 1 gigahertz. So here out of this, we can go with the option P3, that is option C. The next, a file system with 300 gigabyte disk uses a file descriptor with 8 direct block addresses, 1 indirect block addresses, and 1 doubly indirect block addresses. So the size of each disk block is 128 bytes. And the size of each disk block address is 8 bytes. So the maximum possible file size in this file system is what? So I need to calculate. So each block size, it will be what? 128 bytes. So each disk block address will be what? 8 bytes. So each disk can contain what? 128 by 8, it will be 16 addresses. So the size which is due to this 8 direct block address, it will be 8 into 128. Again, the size due to 1 indirect block address, it will be 16 into 128. And the size due to 1 doubly indirect block address, it will be 16 into 16 into 120. And the size due to 1 doubly indirect block address, it will be 16 into 16 into 120. So the maximum possible file size, it will be what? I am going to add everything. So 8 into 128 here, and 16 into 128 here, and 16 into 16 into 128 here. So lastly, we'll be getting this 35,840. So 35 kilobytes. Okay. And here the question here. The size of the physical address space of the processor is 2 power p bytes. The word length is 2 power w bytes. The capacity of cache memory is 2 power n bytes. The size of each cache block is 2 power m words. For a k-way set associated cache memory, the length in number of bits of the tag field is what? So I need to have this option. So this is like the formula. So we are going with this option B. Okay. So next the question here. Next the question here for compute. For computer based on 3 address instruction formats, each address field can be used to specify which of the following. So S1 are memory operand, S2 are processor register. S3 are implied accumulator register. So for computer-based three-address instruction format, each address field can be used to specify what means both S1 and S2. That is our memory operand as well as our processor register. So either S1 or S2. So like this, we having many set of questions. We having many websites under Geeks for Geeks. Like that, we having many websites where we can see to these take questions also. Prepare well, which is very important.